All right, here's a picture of a Air Force T-38 that we captured with sonic booms a couple of years ago. If you look at this picture, it kind of looks like a boat on the water, right? So you've got a lot of the wakes here. So what a sonic boom is the pushing, it's traveling faster than the air is able to get aside, not different than a boat wake. So you could fly slow enough, or you could, on the water, you can travel slow enough that you don't create wakes. Once you go fast enough, you would create wakes in the water, and you get the same thing in the air, except in 2 dimensions, it's in 3 dimensions. So here's some other pictures. So here's our 3-dimensional. You've got shock waves coming off in a cone shape, and not just off to the side like you would on a boat. So here's a T-38 from above. Here's one from the side. And I'll talk a little bit more about some of these pictures here in a second. One interesting thing, some people may think that you only get shock waves when you're breaking the speed of sound. That's not true. You get shock waves as you are continually flying above the speed of sound. What we have here is the carpet that we're developing when we're going supersonic. So this is a good illustration of the carpet going across the ground, following the aircraft. When they pass a person on the ground, that person is going to hear the shock wave. That's why you'll hear a shock wave over a wide area, but not at the same time. It's going to flow through the area. All right, let's talk a little bit about those shock waves and what's happening and how they get to the ground. So this is a real picture of a T-38. Notice you'll have many shock waves coming off the aircraft. As the area of the aircraft gets larger, a shock wave develops. So you can see there's probably around 12 to 15 shock waves right near the aircraft. As they travel down toward the ground, these shock waves coalesce or group together. So right here we're seeing maybe 3 or 4 shock waves. So similar to what we're seeing here, that same thing happens to the point where the shock waves only develop into 2 when they hit the ground from a higher altitude. What we have here is the change in pressure over time. So that change in pressure is related to an acoustic or sound level. So that's where you're getting the quick, sharp change in pressure once and then again on the back end, and that's that boom, boom that you hear. One other thing to point out when we talk about N waves, you'll notice this pattern kind of looks like an N. So that's why we call it an N wave signature for our current supersonic planes that are flying around. All right, let's talk a little bit more about an N wave and then what we can do in the future to reduce the sound level. So this is the pressure change over time, like we described the N wave with a boom, boom. This short little time from here to here, basically between these 2 points, is called the rise time. That's the amount of time it takes to go from regular pressure level or standard atmosphere level up to the boom, the change in pressure for the boom. And that is your pressure change, okay? What we try to do is increase this rise time, so make it longer, and then decrease this pressure level to something less. And that's how we will attack making the boom less loud. So it's important to understand that as we look at some of the waves that we're going to capture today and during this week. All right, for this kind of test, we have an F-18 that's flying up to 32,000 feet. It's got all these shock waves coming off the plane. As it works its way down, the shock waves coalesce into 2. Here's that boundary layer we're talking about. We're typically seeing it between about 3,000 and 6,000 feet is the start of this layer. Our TG-14 motor glider we have flying right above it to capture these shock waves here just above the turbulent layer. And then down at the bottom, we're not going to see a pure N wave, as I'll show you in a second. You'll see some spikiness and some reduction, which is what the turbulent layer is doing to the boom. All right, so this is actual data. This is an N wave, as we discussed before, from the TG-14 up above the turbulent layer. So it kind of looks like an N. Now here's a wave we recorded on the ground. So it looks generally like an N, but you can see a lot more spikiness in these areas. And that's created by the turbulence on the ground. When this pressure goes up higher, that's going to be louder, the spiking. If it gets cut off at the top and gets lowered, that's going to make it less loud. To better understand this is an analogy that's pretty decent to understand the basics. It's not exactly the same characteristics. But if you can imagine a pool, so you've got a pool rippling on top, you can see that there's areas of light where it's really light, and then there's areas that are darker. The lighter areas would be similar to a louder boom. The darker areas would be a softer boom. So this is a good way of representing an entire area over the ground, and why it's so hard to measure this, and why we need to fly so much. So in order to characterize this, we're measuring one location of how turbulent it is overall, and then we're recording booms across an array through here, and then that array is going to see different levels of pressure. So we need to do a lot of boom recordings on the ground and a lot of flights. So statistically, we can figure out how much that boom varies with different turbulence levels. Okay, on to the flight research that we're conducting here. One of the things we're trying to do is validate our code or our models that tell us how the sonic boom propagates through a turbulent atmosphere and how much it can change. We're going to use these actual test flight results to go back to the computer code and make sure it's correct. And then we'll use that to predict the loudness of low boom designs that we have in the future. And yes, this is called SonicBAT, for sonic booms in atmospheric turbulence. Before we came out here, though, last summer we were out at our home base at Armstrong Flight Research Center on Edwards Air Force Base. Here's a picture of what it looks like with the dry lake bed, and Armstrong is right in this area. So what we tried to do there is to record data in a hot, dry environment with varying levels of signatures. We used an F-18 to generate the booms. We had 3 microphone arrays on the ground and to record the booms on the ground. We used a TG-14 motor glider to record the booms above that turbulent layer. And what we would do is turn the engine off so it's pretty quiet flying, record the booms, and once we heard the boom, we'll turn the engine back on and climb up to the altitude. So that's a great plane to do that kind of activity. We also recorded a lot of different weather data to characterize how that atmosphere at low altitude was turbulent. For us, it was just over a year ago, about 10 days of flying between July 11th and the 22nd of 2016. We flew 20 flights and had 64 sonic boom passes during that time. We utilized 2 F-18s, just like we're doing here, and a TG-14. Interestingly enough, that TG-14 flies about 100 miles an hour, and we've taken 5 days of flights to get it out here instead of taking it apart, which probably would have taken a month. So it'll be you'll probably get to see it today. You can see this is the team. We have a similar sized team here for this particular round. All right, so here's some results from that test as we talked about before. So once again, this is the pressure change over time, and what you're really seeing here is each one of these colors is a different microphone spaced at 100-foot spacing. If you look at this sort of run, the average peak pressure should be right here, 1.6 pounds per square feet. So you're seeing a lot of spiking here. And before I talk any more, pounds per square feet is not a number that a lot of people are used to, but you probably know PSI, or pounds per square inch. 1.6 pounds per square foot is approximately 0.01 PSI. So it's a very, very small pressure change. If you look at your tire pressure being about 30 PSI, we're looking at 0.01 change on these pressures here. We also found areas where the shock waves were a little bit less loud. This is the rounding that we're talking about, and that reduced the loudness of the shock waves. And I forget, Ed Herring, our principal investigator, always likes to say, this amount of pressure change is about 2 flights of stairs. But it happens so quick, that's why you get the loudness. Okay, now moving on to what we're doing here. So we're flying out of the shuttle landing facility here at KSC. In fact, we are in this location right here in the ops building. We're going to record a similar data set that we recorded out at Edwards, except we want to be in a humid climate. Humidity has an impact on shock waves and also on the turbulence, so we want to see the difference between what we recorded at Edwards Air Force Base and what we've got here. Our approach is the same. We're going to have 2 microphone arrays rather than 3, and we've added some new weather equipment that's going to help characterize the humidity in addition to the turbulence. We're kind of in the middle of the flights right now. We planned 2 weeks, 10 days of flights with some backup flights in case there's weather or hurricanes or maintenance issues with the aircraft. So far we're doing really well in getting our flights done. We're trying to fly between, the booms occurring between 10 a.m. and 9 p.m. We already had a flight at 8:30 on Monday. We may have another one as early as that later on, but we're still determining that. Oops. We're looking for a minimum of 33 booms, but we want to see different turbulent levels. We want to look at a high, a low, and a medium turbulence level. So even though we reach 33 booms early, we might not have the right mix. And right now we are not finding a lot of high turbulence areas, so we might have to extend past those numbers of booms in order to get that. We have 2 F-18s and a TG motor glider, and like I said, we're flying from this facility right here. All right, so the boom footprint. We have a program that is based on the aircraft speeds, altitudes, and the weather from where the aircraft is flying down to the surface. We can figure out what the boom footprint looks like. These are all different pressure levels here. So based on this sort of picture that we calculate each day, based on forecast winds and temperature and other weather, we're trying to keep the boom foot off of the Titusville and the other cities along the coast. What we did is took this footprint, and that's their main area of booms, and just in case there's changes in forecast, we added a little buffer zone to make people aware that they could hear booms in that area. And it sounds like some of that is happening. We are getting a few booms in Titusville, but once again, we're trying to keep that off based on the daily weather in that day. Okay, as far as what we have on the ground here, we're in the ops building at near this hangar. We're going to go out to the center of the airfield where there's a big shuttle mock-up and the tower. Just to the east of that, we have a microphone array, 1,500 feet long, 16 mics, 100-foot spacing. We have some weather equipment and weather balloons here. And then we have another array a little bit farther off, same sort of microphones, 16 microphones, about 1,500 feet long. So that's basically the setup. And then we have a command and control vehicle that Kennedy has let us use, so we can have good radio comms with the pilots. I'm not going to go through all these individual pieces of equipment, but there are a lot of different weather equipment, a lot of wind measurement, temperature measurement, and heat flux measurement that we have to capture so we know how turbulent it is. We also are sending up a weather balloon for each flight, so we're characterizing the atmosphere from the surface up above the flight profile of the F-18. All right, moving on to today's flight. A better close-up of the TG-14 and one of our F-18s. And like I said, you'll be able to chance to see this later on, up close and personal. All right, so after this briefing, we'll start heading out to the midfield press site around 10:30. We'll have the TG-14 take off at 10:45. We do that early so we can get up to altitude and set up while the F-18 can climb much faster up higher. And we'll be ready for the F-18 takeoff at 11. Expect that we'll get 3 sonic booms between about 11:20 and 11:35. We see that it takes 6 to 8 minutes per pass to hear each boom. After that, there'll be a low flyover of the F-18 as it returns here. We're going to let it go down to the visitor complex, so we'll fly over the visitor complex, and then it'll come back and land. After that happens, we're going to invite you to come back to this hangar. Once the aircraft shuts down, you'll be able to talk to a few of the subject matter experts and the pilots of both aircraft. And at about 13:30 or so, we expect that we'll let you leave the shuttle facility beyond your day. So if we were a little bit worried about weather, but our forecast this morning looks pretty good. And so I think we're going to have a good mission today based on that forecast. All right, some of the things to look for. So the TG-14 is going to look like this, a little piece of white in the sky. I'll try to point it out if I see it out there. We had a pretty good luck yesterday, and it's going to be at about 4,500 feet to 5,000 feet. So we should have a chance to see it. F-18s are a little bit tougher to see, but once it's up at 40,000 feet, it's going to start to be able to accelerate as it is in its dive, we might see some contrails. Once it dives from 40,000 feet, they'll kind of disappear. We'll also have a chance to see it when it climbs back up after the pass. We're going to do a quick climb up to 40,000 feet, and we might see the contrails. So I'll point that out for you as we're out in the area as well. Yesterday we were able to see it at those 2 times. I'll also have a radio, so we'll hear the pilots talking to our ground controllers. And I've got some speakers, so feel free to listen in on that. Here are the calls that they're going to make. They make a turning in call. That means that they're, get ready, people on the ground. I'm starting to make my way in and set myself up for the run. There's a 2-minute call, and why does 2 minutes not match 3 minutes of boom? There's a point in the sky that we tell the pilots to fly to, and that point is going to allow the boom to travel from there down to the ground to our microphones. Right now the time is about 1 minute from the mark call that we're going to have to the boom on the ground. So if you hear 2 minutes, it's going to be about 3 minutes of boom. 1 minute is about 2 minutes of boom. You'll hear 30 seconds, 3, 2, 1 mark. And Ed, do you happen to know what the propagation time is?
I look it up, it's like 75 seconds, probably the exact number.
Might be a little bit longer than 1 minute, so that was a rough time. We'll let you know that out there, and Ed's done a pretty good job of marking the time and saying the boom will be in 3, 2, 1, and within a second, you should be able to hear it at the site. You should hear that big double boom. If you, I hope you've heard them before. If you haven't, it is a little startling. And people will be jumping, but we're getting good data on the ground. We'll hear the aircraft parameters, how fast it's flying, how much fuel it has remaining, so we have an understanding of how many more passes we can do. And I already talked about the time between booms. And then I talked about the flyby, people had at the end. Okay, so that's what's happening today, but what's happening next? We do have a model on the table of this demonstrator. So NASA is building a low boom flight demonstration X-plane. We just were approved with it, and we'll talk a little bit more about what it's about. But before we go there, there was a ban from the FAA on supersonic flight from Concorde and the proposed supersonic transport back in the early 70s. So since 1973, both the FAA and the International Civil Aviation Organization, which is the international version of the FAA, have banned supersonic overland flight. You can do it over water, but not over land. We believe at NASA that the standard should not be a speed standard, but should be a sound standard, just like everything else. So we are working towards helping provide data to these organizations to set the standard. So why do we want to fly supersonic versus flying our 0.9, 0.85 Mach flights we currently have in airliners? Well, in some cases we can get to places about twice as fast. And for those that travel, that is a huge difference. Do I really want to spend the whole day going out to California? Or if I can travel out there and be back in the same day, you might be more than likely to do that. So it's valuable to a lot of people in the U.S. It is also an opportunity for the U.S. to continue the lead in the aviation industry and not let another country take over. That's one of the few places where we are still in the lead. We believe there is a large market potential for both business type aircraft and civil airliners if we can make the sound, the right sound level for these booms. And like I said, there's a huge impact that it could have in the U.S. Also, while we're working on our research, there are a lot of companies that have or are continuing to do research in supersonic flight. Most of these are not low boom, but they are learning how to go supersonic, and that's part of what they're trying to do in the future. But if we can set a standard, I think a lot of these companies will jump in and they will start designing to that sound standard. But no one is willing to start designing to a sound standard that may not be allowed in the future. So why demonstration? One of the things the FAA and the ICAO want us to do is collect data in communities and see how annoyed people are at different sound levels. We don't have a plane that's low sounding enough with sonic booms right now. So in order to get that sound level, we're building a plane that can be at a pretty low sound level, and we can increase it and figure out what the annoyance level is for each different loudness level. Once we collect that, we will give that data to the FAA, and they will decide based on our numbers what they think we can accept. And it'll be we're not a regulation organization, we're a data organization, but we have been working with the FAA and we will be providing that. We do have a neat maneuver that we learned in California. I think Ed Herring, once again, found this and started this. If we do a rollover dive with an F-18 over a small area, we can get a low sounding boom. It's not a shake boom like I talked about, but a lower amplitude in wave. And based on that, we have in the past done superior response in areas that are custom to sonic booms. But this is something else we might try again this next year in one of the areas over the US. That's all leading up to using the low boom flight demonstrator in the future as a way to gather data. Okay. So one of the things I was talking about is how to measure response. So if you think about the in wave we had before, this wave is much lower in amplitude and it has a longer rise time. So the sound level coming off of a future plane is going to be much less. We have shaped parts of a plane before, but you're only seeing part of the sound level. The rest of the plane is still loud, so we really can't use those types of planes to get this data. We need a nose-to-tail aircraft that is low boom. We also need to conduct this over many communities. We're looking at 4 to 6 in the future. And as we said, this requires a research platform. So a better look at what I was talking about before. Here's where the Concord was at 2 pounds per square foot. We're looking at much less and a shorter rise time. So what this plane should be capable of doing is if you were having a normal conversation, you might not even notice a boom happening outside. If it's really quiet, you'll hear something, but it's not going to be like the booms you're hearing today, for sure. Okay, so where are we on the low boom flight demonstration? Lockheed Martin was contracted to develop a preliminary design. This has been called QUEST, Quiet Supersonic Technology. In the future, it's going to go back to being called low boom flight demonstration. The preliminary design review was held in June. This contract should be over in the not too distant future. And we released a request for proposal to other companies to do the final design, manufacture, and test of the aircraft. The timeline for this, and remember these dates are all subject on funding and not having any slips due to technology or other reasons. But we expect the design and build contract to be awarded next year. Our first flight will be in 2021. We're going to do some work out at Edwards or Armstrong Flight Research Center in 2022 to understand if the acoustic signature is what we predict. And then we expect to fly out of that location on an initial community response test. Following those tests, we expect over the next 3 years to take them around the country, looking at 2 to 3 communities per year. All right, so how does SonicBAT go back to the low boom flight demonstrator? I think I alluded to it, but we have a pretty good idea how booms are modeled minus turbulence for the low boom flight demonstrator. This is one of the first tests where we've measured booms and turbulence, but also measured really good weather data so we can kind of correlate those. So using that, we can build a model for in-wave type aircraft or the current aircraft. Then we'll use the same model to propagate the low boom signature that we have in the future. And then once we get the low boom flight demonstration flying later on, during that acoustic testing in 2021, 2022, we'll compare it against that and make sure our model matches what we're seeing on the low boom flight demonstration. That concludes my brief. I'm opening the floor up to questions now and realize you have several other opportunities to answer or to get questions answered throughout the day.